Now, interestingly, the farther away something is, the less it will seem to shift. If I look at some light on the Monterey Peninsula off across there, and I say, right now it's in that direction, and I take a step this way, well, it's still in pretty much the same direction. With a sensitive enough optical instrument, I can tell if it's shifted a tiny fraction of a degree, but it's not nearly as easy as it is for me to tell that that close by object, the chair, has shifted. Well, people told Aristarchus, dude, if you were right, if the sun were the center of the solar system, and the Earth were actually revolving around the sun, well, the thing is, if you ask the scholars at the time where the stars are, they thought the stars were just kind of out beyond the orbits of the outermost planets, that they were a little bit farther away than the sun, maybe 2 or 3 times farther away than the sun, but they thought the stars all lived on this giant crystal sphere. In fact, they thought the crystal sphere was an actual physical object. It wasn't a metaphor or anything like that. They all lived on this giant transparent crystal sphere. When I say lived, they didn't think the stars were alive. The stars were all fixed to this giant transparent crystal sphere out here. And it was probably, they thought, about 2 or 3 times farther away from us than the sun is. So they made the very good point. Look, go out tonight and measure the angle to some star in the sky. Pick Polaris if you want. Polaris is a nice one because it's not going to rotate around in the sky from moment to moment, so you don't even have to worry about that. So measure the angle to Polaris. Then wait 6 months. And they said, Aristarchus, you're telling me that 6 months later the Earth will be way over here. Well, look for yourself. Measure the angle to Polaris. If the Earth had moved, that angle should shift. You should see, in other words, some stellar parallax, some parallax of the fixed stars. And, of course, they knew when they told him that, no, you don't see that. The stars seem to stay in the same position in the sky season after season. Their elevation above the horizon changes. We know that it's because of the tilt of the Earth's axis. They kind of thought it was a kind of tilt of this entire celestial machine that was going on. But they said the position of the stars relative to each other, or the absolute position of Polaris, those never change. And because of that, that means the Earth cannot be orbiting around the sun. Instead, the Earth must be standing still at the center of the universe. The sun's orbiting. If there was somebody living on the sun, they could see that parallax effect. But here on the Earth, we can't. Now, this is why I think Aristarchus was such an awesome astronomer. It's not because he was, he believed the sun was the center of the solar system. That could have just been a lucky guess. That doesn't really mean he was better at interpreting evidence. But it was because he was willing to change his model in the face of arguments like that. Because he listened to that argument and he said, you're absolutely right. What that tells me, though, is not that the Earth is the center of the universe. That tells me that star, Polaris or any other star, must be a hell of a lot further away than any of us imagine. And he said, okay, the Earth is orbiting the sun. I'm sticking by that. But the fact that that star does not change angle, the lack of stellar parallax, I'm not going to take that to shoot my model down. I'm just going to revise my model. I'm going to now say, okay, all those fixed stars have got to be incredibly distant objects. So distant that I can't measure the stellar parallax even by my best efforts. Hey, today, by the way, we can measure stellar parallax because we got much better telescopes. And it turns out, yeah, the nearest star, Alpha Centauri, is about 4 light years away from us. We know that now by a lot of different methods, but the first way we learned that was actually around the year 1800 is when people first became able to actually measure the shift in position of nearby stars relative to the farther away ones as the Earth orbited the sun. So that was a pretty impressive accomplishment. They couldn't do it in Aristarchus' day, so he just said, hey, all that means is the stars are seriously far away. And hey, by the way, if they're seriously far away, they must be seriously bright. I mean, we knew they were already pretty bright because I could see them at like 2 or 3 times the distance of the sun. But man, they might be as bright as the sun itself, which of course was absolutely true. Yeah?
Do you know what angle change they witnessed in the 1800s?
Well, let's see. Alpha Centauri is 4 light years away from us. Sirius was actually the first one that they made the measurement on because it's a brighter star, easier to measure, and it's 10 light years away from us. The Earth is 8 light minutes away from the sun. So from our position on one side of the sun to the position on the other is 16 light minutes. So what's the ratio there? 10 light years to 16 light minutes. Well, a year is about 30 million seconds. A minute's 60 seconds, so there's about 500,000 minutes in a year. So if you take, 16 light minutes, 500,000 over 16 gives you about 30,000. And then we're doing 10 light years, not 1 light year. So the distance that we shift position over that 6-month period is about 1/300,000,000th of the distance to Sirius. So how much does Sirius shift by? 1/300,000,000th of a radian. What is that in degrees? Well, that would be about 1/300,000th, I'm sorry, not million. 1/300,000th of a radian. In degrees, that would be about, divide that by 60, about 1/5000th of a degree. So that is the angle shift that they were able to measure in 1800. My hat is off if I were wearing one to the astronomers of the year 1800 who managed to measure. So yeah, no shame to Aristarchus that he could not make that measurement using those devices. So yeah, with those instruments, he was not going to be able to measure the stellar parallax. And he said, no problem, that just means the stars are vastly farther away than any of us knew. And that conclusion that he reached, I mean, not only is it right, but I just admired his ability to say, yeah, you know, I do have to either discard my model when you come up with an objection like that, or I've got to modify my model to take it into account. And he was able to. And he, you know, as it turns out, he's right. The stars are vastly far away and vastly bright. But it wasn't just stumbling on the right answer. It was the logic that led him there that I really admired. All right. Any other questions on this segment? Yeah.
What was the first group proposing the crystal ball idea of the tracking?
It seems like that was kind of the consensus of all the philosophers of that era. So I don't know who first proposed that series of concentric crystal spheres. It wasn't just one crystal sphere out there. What they thought was the Earth is at the center of the universe. The moon is on this closest crystal sphere. And the moon's attached to the inside of that transparent sphere, and the sphere carries the moon around in its orbit. And then they said the sun is on another crystal sphere, considerably further away than the moon. Aristarchus' measurement told them how much further away. A little bit wrong, but fine. They thought the planets are each on their own crystal sphere. And the planets were moving in complicated ways. I'll show you Ptolemy's solution to that problem in a moment. But the planets, they thought, were doing some pretty crazy things. But each planet had its own crystal sphere. And then outside the crystal sphere of the outermost planet, which they probably would have agreed with, like Saturn or Jupiter, you'd have the sphere of the fixed stars. They call that one the firmament. So if you hear that word firmament in old documents, that's what they're talking about, that outermost sphere of fixed stars.
And kind of like a crystal like running through the star, like running through the planets, or almost like a two-dimensional thing.
Like a soap bubble. I mean, when I say it's a crystal sphere, it was because it was entirely transparent. So you couldn't see the spheres. You couldn't even see reflections off of them. But they learned how the Earth is here, and a soap bubble around us for the moon. And the moon's just a point that's moving on the soap bubble. It's fixed, so the soap bubble's spinning, and it's carrying the moon.
Almost like a two-dimensional point on the bubble itself.
And by the way, yes, exactly. And by the way, they did not think that the Earth was rotating either. They considered the possibility and rejected it, in part based on Aristotle's physics. They said, what the hell force could keep this big ball of solid matter rotating? It doesn't take a force to keep something rotating, but they didn't know that. So they actually thought this entire machine of crystal spheres rotated around the Earth once every 24 hours. They didn't think the Earth is rotating, that makes the sun rise and set, but they thought the sun and the moon and the stars and everything else, this entire network of interlocked crystal spheres were all rotating every 24 hours, and then on top of that, they would make slower motions that gave the the orbits of these objects, the monthly orbit of the moon, the yearly orbit as they saw it of the sun, and so forth. Yeah.
What force did they think was rotating the firmament?
It didn't take a force to rotate the firmament because it was made out of ether, so it didn't need a force. So yes, only solid objects took a force. And Aristotle had all the angles covered. And then sadly, I got to do a little joke about 400 years before the next big entry in this story. It's not that nobody was making interesting observations over the next 400 years, but there were no really really new novel discoveries to report until Ptolemy, an Egyptian astronomer, in the year AD 150. According to some writers, Ptolemy was actually the king of Egypt. I'm pretty sure he wasn't. There was a king Ptolemy around the same time, but I'm pretty sure that biographers from hundreds of years later who were writing about King Ptolemy and said he was said to have been very wise in the ways of astronomy. Now, they were just mixing up Ptolemy the king with Ptolemy the astronomer. It's very unlikely that the king would have had time to make these extensive measurements of the skies like Ptolemy the astronomer did. Why do I say he made such extensive measurements of the sky? Well, he was the first one to do a serious systematic study of the motions of the 5 planets that they were aware of. Of course, Earth isn't on the list because they didn't think it was a planet. They thought it was the center of the universe. And Neptune and Uranus are not on the list because they're too dim to see with the unaided eye. Pluto is way too dim to see with the unaided eye. Whether or not it's still a planet, I leave to everybody's judgment. So these were the planets people were aware of. And why did they think they were remarkable and worth studying? Well, because as these fixed stars all kind of move together, rising and setting each night, the planets would wander from point to point in that star field. The word planet translates as wanderers, so the planets seem to move around against that background of fixed stars in unpredictable ways, according to the ancient astronomers. In fact, this might be why they always name the planets after mythological figures, gods and heroes and stuff, because they said, hey, we're naming the planet after actually living, self-willed beings. I don't think they thought that the planet Venus actually is the goddess Venus wandering around in the heavens, but they said, it makes sense to name the planets which seem to have a mind of their own after creatures that do have a mind of their own. Well, Ptolemy said, no, the planets do not wander around at random. You can actually make a systematic study and predict where they go. And his system was pretty interesting. He still did believe in Aristotelian physics. He still did believe in this network of concentric crystal spheres. You could say his observations might have given him the evidence he would have needed to question that model. But as it turns out, no, he just modified the model to take his observations into account. Now here I am being a hypocrite. I mean, I say Aristarchus was awesome for modifying his model to take observations into account. I'm saying, Ptolemy, man, I wish he had been willing to throw the model out altogether. Well, it's probably just me kind of rooting for the one that I know would eventually lead us in the right direction. But Ptolemy to me is a heartbreaking figure who could have figured things out over 1,000 years before they really were figured out, but took the wrong path. I'm going to show you a brief clip from a History Channel documentary on Ptolemy. I know, the History Channel is drift these days. It's awful. I wasn't joking about did Bigfoot build the pyramids. However, this documentary is actually really well done. This reminds me of what they used to be.
In more detailed information about our dominant celestial neighbors, the sun and moon.
Even back then, 2,000 years ago, they knew that the Earth curves. And by looking at the shadows, they calculated the size of the Earth to within about 10% accuracy. They actually calculated the distance from the Earth to the moon and the rough dimensions of the distance from the Earth to the sun. So in other words, the ancients were no fools.
By the way, that is Michio Kaku there, who's also no fool. He's an awesome, the moment I saw they had Michio Kaku willing to speak on this documentary, I knew this was not the usual History Channel.
The ancient Greeks also recognized 2 types of stars. Most were fixed and small and moved together.
That crazy flash, that was just some intern deciding we should put a big flash of light in there. They're not saying that anything actually happened. They're also not saying the planets move real time like this. They're showing you if you observe the planet night after night against that background of fixed stars, this is what you would see it do.
Few were larger and moved haphazardly, or so it seemed. These were planets, and predicting their motion became essential.
That's how the planets seem to turn around and go the other way for a little while. That's called retrograde motion, and that was part of what Ptolemy was trying to explain with his model, is how the hell that can happen. If you've got these spheres rotating around the Earth, why would it suddenly seem to rotate backwards and then start the same way again?
its long goal. With just their naked eyes to scan the skies, the Greeks saw only 5 planets, naming each after their gods. Today, we're more familiar with their Roman designations: Mercury, Venus, Mars, Saturn, Jupiter. Ancient astronomy assumed a concept of the universe proposed by 4th century BC Greek philosopher Aristotle, who imagined the Earth at the center of the universe, with the sun, moon, stars, and planets all revolving elegantly around it in perfect crystalline spheres.
So there you go. There's that crystal sphere model. That's part of the reason I wanted to show this clip, is because with my whiteboard scrawlings, I cannot do justice to the crystal sphere model. There is kind of, I mean, obviously not to scale the relative sizes of all these things, but there's what they thought the universe was structured like, with the Earth at the center. And again, I can't emphasize enough, they thought the Earth was not spinning on its axis, but this entire machinery of crystal spheres turned every 24 hours. And then on top of that, you had individual rotations for each sphere that would carry out the orbit of the thing that was attached to it.
Bubbles' universe was finite. It was a big sphere. Actually, it was like onion. It was an onion with many concentric spheres.
1st century astronomer Ptolemy improved on Aristotle by accurately tracing the paths of the planets, which didn't move haphazardly after all. Using complex circular motions called epicycles, Ptolemy could predict their prescribed paths and changing velocities.
You notice there's the sun. It's the one thing that's not doing those crazy curly-Q epicycles, because that's the thing that's actually fixed. So the only effect we're seeing for that is the effect of the Earth's motion. All the other planets, they are moving in giant circles, which would represent their actual orbit, and then superimposed on that, you get those little curly-Q epicycles. Well, that is the effect of the fact that we're standing on a moving platform. So those epicycles are tracing out once per year, because the Earth is orbiting around the sun once per year. So if we don't know that we're moving, we project our motion onto all those other objects.
In other words, Ptolemy's system reliably predicted the future behavior of the planets, another step in man's journey to understand and control the universe.
The Ptolemaic system was extremely complex. It had all these planets going in loops, and it worked beautifully, but it was just wrong. The idea that you can predict something doesn't mean you understand the fundamental principles behind it.
So yeah, I like that. The idea you can predict something doesn't mean you understand the fundamental principles. Ptolemy's model was brilliant at predicting where the planets would be. At this point, you could say, hey, 512 years from now, on March 23rd, 7:38 p.m., where would I look to see Venus in the sky? And Ptolemy could tell you. So I mean, in that sense, this was a remarkable accomplishment. At this point also, they didn't mention this, but this is when the orbits were plotted accurately enough that we could start to predict things like lunar and solar eclipses. So, Ptolemy added a lot of predictive power to what had been known before, but his basic picture of what was going on stayed askew. He still thought the Earth was the center of the solar system, and you had this complex network of spheres within spheres around it.
Ptolemy's system did not accurately reveal the universe, but it didn't try.
He essentially showed that the positions of the planets could be calculated for any time past or future. It was a tour de force of mathematical understanding. Interestingly, the astronomy seemed to stand still for centuries after that.
In fact, after the collapse of Rome in 476 AD, astronomy actually lost ground.
Okay, that part's false. Rome did collapse in 476 AD, that's true. The Library of Alexandria was burned for the final time just before that by a mob of zealots. And that was also a vast loss to the accumulated knowledge. So in that sense, there was a sharp downturn in what we knew about astrology, or astronomy, I'm sorry, because so many of the records in the books had been lost. However, when they talk about how then the next several, 800 years in Europe were the Dark Ages and no progress was being made, that is a very Eurocentric viewpoint. It is true, in Western Europe, the universities closed when Rome collapsed. It was hard to get an education. If you wanted basic literacy, about the only place to go would be to join a monastery and become a monk, and they would teach you to read. But there wasn't a whole lot of astronomical investigation going on. In fact, one of the awesome astronomical events of kind of the next few hundred years, the supernova whose light reached Earth in 1054 AD was recorded in China, was not recorded anywhere in Europe. Apparently people just were not writing down what they saw in the skies. So yeah, if you're just limiting yourself to Europe, then yeah, the knowledge had regressed somewhat. However, the thing we call the Dark Ages in Europe is also known as the Golden Age of Baghdad. If you move a few time zones east, there was another thriving academic culture going on, again centered in the city of Baghdad, and the Great Library of Baghdad had become the more modern replacement for the Great Library of Alexandria that had been burned down. And scholars were traveling from all over the world, including Europe. So when I said that one of the paths to literacy in Europe was to go join a monastery and learn to read, if you were up for the journey, a more awesome path perhaps, was go to Baghdad, join the Great Library there, and you can not only read, but you can do cutting-edge science there. Astronomy was thriving, mathematics was thriving, biology, the first sense of a form of medicine that was more likely to cure a patient than to kill them was starting to be born there. However, throughout the Great Age, the Golden Age of Baghdad, observational astronomy made great progress, instrumentation made great progress, but that Ptolemaic system of the Earth at the center of the universe and those concentric spheres around it, which dated back to Aristotle. And by the way, Aristotle and the Greek and Egyptian philosophers were still intensively studied. What records had remained after the burning of the library in Alexandria ended up in Baghdad. So you could still study all the ancients we've talked about. That knowledge had not been lost. However, they also did not find a way to break free of that Ptolemaic system. Back to this benighted person who didn't know any of that happened, but the next stage of the story still needs to be told, because you'd still say, all right, well, in that case, we still need to know how are we going to get that idea of the Earth at the center of the solar system out of the public consciousness.
Europe fragmented into smaller powers, and a lot of the wisdom of the Greeks was lost.
1,000 years later,
And you notice, we did that gap of 400 years before Ptolemy. Now we are doing a gap of 1,000 years. It's not that nothing happened. The Golden Age of Baghdad happened. That was pretty damn impressive. However, by the time we're talking about now, which is getting to about the year 500, the Library of Baghdad had been burned. Genghis Khan's grandkid swept over and invaded Persia, sacked the city of Baghdad, burned the library, burned the books, killed a lot of the scholars who lived there. So that academic culture never really recovered from that. Universities reopened, but instead of this one thriving center that everybody wanted to go to study together, it was smaller universities at various towns, and also there was a lot less openness to new ideas. During the Golden Age of Baghdad, you could be a scholar from any culture, any religion. If you could make your way to Baghdad, you were welcome there. I mean, they probably argued and tried to save each other's souls and all that kind of thing. But for essentially, religion and science were just considered two different things. Everybody could get together and do science together, even if they disagreed on other fundamentals. After Baghdad was rebuilt, after Genghis Khan's grandkid went away, the economic times were a lot worse. People tend to get, dig in their heels and get very hard-edged in their views during bad times. And essentially, you were no longer welcome if you weren't willing to toe the political line, the theological line, and everything else. So the universities had reopened in the Mideast and Northern Africa, but it wasn't quite this awesome time of discovery anymore that it had been before that invasion. People gotta quit like sacking cities and burning down libraries. It sucks. So now we're back in Europe. Europe is picking themselves up after the Dark Ages, and they're telling us the story of a Polish astronomer, Copernicus. And again, while a lot of things had happened in the intervening 1,000 and some years since Ptolemy, the Ptolemaic system was still the state of the art as far as astronomy was concerned.
A new theory would confront accepted beliefs about how the heavens worked, and would move mankind one step closer to a theory of the Big Bang.
I'll show you a bit of the clip on Ptolemy.
During the 15th century AD, an idea called heliocentrism claimed the sun, not the earth, was at the center of the universe.
No, it's not the first time that idea had been proposed. This was Aristarchus' idea from way back before. Copernicus, the Polish astronomer, is going to take up that idea, and I like the graphic they're about to show of how Ptolemy's worldview would change if you redo your calculations with the sun at the center of the solar system instead of the Earth.
This horrified Christian clergy, who felt it contradicted the word of God. If God created earth and man in his own image, then earth and its devout inhabitants must be the center of everything.
They're probably overstating that case. At the time Copernicus lived, there was not a hell of a lot of religious opposition to his ideas. He was considered kind of a crackpot among astronomers. I mean, the idea the sun was the center of the solar system was not an easy one to accept. But among the people who were urging Copernicus to publish his book, I want to read this model you're putting together, was the Pope at the time. So, I mean, it's not like there was fanatical religious opposition to what he was doing. There would be within a couple generations. One of his students, Bruno, was burned at the stake in the year 1600, in part because he was pushing the Copernican idea. Galileo narrowly escaped being burned at the stake, in part because he was pushing the Copernican idea. So I'm not saying that the Inquisition was a benign bunch of flower children or anything like that. But during Copernicus's lifetime, he did not have to worry about all that much violent opposition from the church.
Ironically, the champion of a sun-centered universe was a devout church deacon from Frombork, Poland, named Nicholas Copernicus.
He was a cathedral administrator, working to help collect the rents, helping people who were sick. But in between, he was working on astronomy.
Copernicus was troubled by Ptolemy's complex heavenly mechanics. But he found an elegant solution. When he moved the Earth from the center of the solar system, and replaced it with the sun at the heart of it all.
Okay, so it wasn't quite so easy as moving the models around on this big giant spinning thing. However, what he did was he recalculated all those planetary orbits, and he said, instead of trying to calculate where each object is relative to the Earth, let me calculate where it is relative to the sun. And one of the big reasons he could do this was that during the golden age of Baghdad, one of the fields of mathematics that had come into being was three-dimensional trigonometry. Two-dimensional trigonometry had been advanced during the Greek and Egyptian times, but at this point you could do spherical coordinates, you could transform from one coordinate system to another, figure out where something would be if viewed from a different point in space. He did this with all of the best existing data on the orbits of the planets, and what he found was...
When Copernicus put the planets going around the sun, he discovered that the planet Mercury, which goes around in about 3 months,
In other words, what we just saw was those crazy curlicues went away and were replaced by a system of perfect circles. In fact, that's where I think I want to pause the video for good, is on that system of circular orbits. Now we know the planetary orbits are not quite circular, they're actually ellipses. That would be discovered about 100 years after this by Kepler. The data at the time wasn't good enough to detect that they're not quite perfect circles. So as far as Copernicus could tell, the best data available to him, by the way, they still didn't have telescopes, which was why they still hadn't discovered Neptune or Uranus. Those are planets that are bright enough that you can see them with a low magnification telescope, but you can't see them with the unaided eye. They were still doing unaided eye astronomy. The instruments had gotten way more advanced than those primitive ones I showed you from back in Aristarchus' day. Tycho Brahe, only a few decades after this, had this observatory where essentially you had these giant protractors in 3 dimensions where you would sit in the center of this crazy machine full of wheels and you'd fix the crosshairs of the device on whatever it was you wanted to look at, and you'd turn so that it was lined up and the wheels would all go click, 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 and you'd read off the numbers on the wheels and they would tell you exactly where in the sky that point was that you were looking at. Angle above the horizon, angle east or west of the north-south line. It was beautiful. However, you still couldn't magnify anything. You had to be able to see that thing that you were looking at with the unaided eye. Then you could use these sophisticated instruments to track its motion. But yeah, this system, to the best data they had available, man, this was so damn simple compared to those crazy curlicues. By the way, we didn't really talk about where the curlicues came from. What Ptolemy had thought was going on physically out there with the planets is that, yes, they are each fixed to a crystal sphere that's rotating, but the crystal spheres for the planets have smaller spheres that are rolling around the inside of them, and the planets are actually fixed to a point on that smaller sphere. In fact, one improvement they had made to Ptolemy's model during the Golden Age of Baghdad was they realized, no, if you look closer, you've actually got to do 3 spheres. You have the planetary sphere, so for Saturn, you have the sphere of Saturn, and then you have a smaller sphere, which is carrying Saturn through its epicycle, and that's rolling around on the main one. And then you have a smaller sphere inside that one to make corrections to that. So it was this crazy, complicated system of multiple interlocked spheres. What did Copernicus replace it with? These perfect planetary orbits. Now, nonetheless, Copernicus was not sure he was right. He famously dragged his feet on publishing this system for year after year, for about 3 decades, when the basis of his system, he had shared the calculations with his friends, he exchanged letters with them. His friends all said, man, you gotta write a book on this. So he did, and he shared the draft of his book with his friends, and they said, are you going to publish? And he said, well, no, not yet. I haven't worked it all out yet. And this actually went on an almost comical length of time. He was over 80 years old eventually, and still hadn't published his book, and essentially said, well, if I don't publish it now, I never will. So he sent his book to the printer. This was right after the invention of Gutenberg's printing press. So you had movable type. And instead of having scribes have to laboriously copy out your book by hand, you send it to the printer, you get back this stack of bound books with the wonderful smell of printer's ink when you open it. And man, if you'd ever been one of those scribes getting carpal tunnel syndrome from the hand copying books, it probably was a wonderful smell of printer's ink, at least assuming he had other work lined up. So they say Copernicus by this time had fallen into a coma. He'd had a series of strokes, fallen into a coma. They brought his book to him, and he opened his eyes and paged through the book and smiled and gave his approval and fell back into the coma and never woke up again. Now, if he was worried about getting in trouble with the Inquisition, that was a brilliant strategy for making sure that you're out of reach by the time the book hit print. But I think that really wasn't his main worry. He just wasn't sure if he had this right or not. Why was he not sure he had it right? A couple reasons. He had done the same logic as Aristarchus and realized that because there is no observed stellar parallax, if the Earth is orbiting the Sun, the stars have got to be seriously far away. You'd think that, man, this is 1,800 years after Aristarchus. People must have already known the stars are seriously far away. No, they still thought they were on that crystal sphere 2 or 3 times farther away than the Sun. So just expanding his sense of the scope of the universe that much kind of blew Copernicus's mind. Some days he was willing to make that claim. Other days he said, what the heck am I talking about? The stars being, thousands of times farther away from the sun and almost as bright as the sun. How the hell could that be true? So there were a lot of times that he thought, no, my ideas are crazy. I would embarrass myself if I put this in print. He also had no answer to the question of, if the Earth is moving, why don't we feel it moving? Because based on Aristotelian physics, the only way you can move along on a moving vehicle is if some force is pushing on you, causing you to stay with the vehicle. He asked, if I jump out of a tree, well, if the Earth is moving tens of thousands of miles an hour, if I jump out of a tree, by the time I hit the ground, the Earth should have moved miles on without me. Why do I hit the ground at the base of the tree instead of miles away from it? And he had no answer to that. The question of how could the Earth, which is definitely a solid object, orbit the sun, what force is pushing on it? Well, again, we say today you don't need a force pushing on it. Actually, you do need a force pushing it inward toward the sun, but you don't need a force pushing it forward to keep it going. So, the answer was the only force that's needed is the pull of gravity from the sun. Well, this is before Isaac Newton. They didn't know there was such a thing as the pull of gravity. And, he asked him, well, if you're worried about what force keeps the Earth moving, how do you explain what force keeps the moon moving? The moon was still thought to be made out of ether, so you didn't need a force to keep it moving. So that whole Aristotelian system of physics was still the state of the art of physics. Physics had not advanced an iota since Aristotle, and this was really getting in the way of Copernicus's ability to make sense of his astronomical model. Now, Copernicus just kind of remained confused till the end of his life. He was sure he was onto something good here, but he didn't know how to answer these objections. So he finally published his book just because he was running out of time, but he still didn't have answers to this. However, things are now starting to speed up again. I don't have to tell you another 1,000 years passed, which is good, because we have to come back like 400 years from now to hear the answer to that. This time, less than another 100 years passed before, well, there were a couple awesome astronomers on the scene in between here. Brahe and Kepler. I told you a little bit about Tycho Brahe. Man, I want to tell you the whole story about Brahe and Kepler, but I'll tell you another time because we're running short on time here. So the next one who absolutely broke open this whole question of how the solar system is arranged would be Copernicus. There's still Copernicus. This gentleman, Galileo. And let's see if it will let us restart the slideshow. Yes, it will. Okay, Galileo was a bit of a jerk, actually. I mean, not nearly Columbus standards of jerks. It seems like 1 nano-Columbus or something like that. But he really liked to pick fights with people. Which is good because at this moment in history, that's what you really needed. You needed somebody who was so orderly and irascible that you could give all of these objections to this model, and they would shrug them off and find a way to push forward anyway. And that was Galileo. He had actually started life planning to be a doctor, or rather his family had planned for him to be a doctor. His family was mostly made up of musicians. His dad was a composer, pretty good one apparently. His brother was a musician, and his brother was just as broke as musicians always are. So in order to pay off the brother's debt and pay for their sister's dowry, they had really hoped that Galileo would go into some field like medicine where you could make a little bit of money. However, he hated medicine. So he was at the university attending a lecture on medicine, and he noticed something weird about the chandelier. They were in a lecture hall, and I guess in the next story up, there was another lecture hall. So all the students tromped in and out of the one upstairs, and the chandelier started rocking back and forth. And then, so he was bored, so he took his pulse and started timing the swings of the chandelier. And the chandelier gradually died down to equilibrium because all the students upstairs had taken their seats. And he keeps timing it, and he notices when the chandelier is doing really tiny amplitude oscillations, it's barely oscillating at all. Well, those of you who have taken physics class, you tell me, when does it oscillate faster? When does it take a longer time to swing? When it's doing big oscillations, or when it's doing tiny ones? It actually turned out to be the same for both of them. And he said, that's weird. It's not like earth-shatteringly weird, but that surprises me. There's got to be some good reason for that. Well, it's a physics problem, so I'll just open a physics book and find out. And he opened Aristotle's physics book, which was the best that was available, and became enraged because it wasn't that Aristotle gave the wrong answer. Aristotle's physics didn't give any way you could even start to answer a question like this. It was just all about the natural motion of this kind of matter and the natural motion of ether and the fire is more rarefied than air, which is more rarefied than water. And it all sounded wonderfully profound, only if you said, okay, cool, how would I calculate the period of pendulum? No, there was nothing in there that would even let you start. And he said, we've been putting up with this for 1,800 years and we can't do any better? No, screw it, I'm not going to be a doctor, I'm going to be a mathematician, and man, I'm going to straighten this out in my lifetime. And, well, so he did. He abandoned the study of medicine, took up mathematics. He did still need to help pay his brother's debt, so he also was a practical craftsperson who invented things. One of his inventions was an improvement on the telescope. Now, the telescope already existed, but it was a tool for navigation, for ship's captains, or for the merchants who are waiting in the port for the ships to come in. And if the ships come in and they're flying flags that tell you what they're bringing and how much they got, the merchant who can see that ship the farthest offshore and know what goods are coming in and what prices are about to drop and what prices are about to rise is going to make a fortune. So there was a lot of money to be made if you could make the best spyglasses, the best telescopes of any of your competitors. Well, he did make damn good telescopes. So he managed to pay off his brother's debt. He also realized, screw looking out to sea and watching those ships, I got a better use for this thing. He turned the telescopes to the sky and immediately opened a whole new realm of astronomy, things that had never been observed before. One of his first discoveries was he looked at the moon and he said, hey, check this out, the moon has geography in it. I mean, I can see little blotches on it with the unaided eye, but those blotches, those are mountains and craters. I can make out the shape of them now. And no, I'm not imagining that it kind of looks like a mountain from this angle, because as the sun hits the moon at different angles at different times of the month, I can see the shadow of that mountain moving around. That really is a three-dimensional mountain up there. Now, why was it so important to show that the moon had geography? Yeah, the moon is made out of solid matter. It is not made out of ether. And that is a shattering blow right there to Aristotle's physics. You know, not only does it mean, hey, Aristotle was wrong about the nature of the moon, but it means solid matter can orbit in a circle. Because look, the moon's solid matter, and it is orbiting in a circle. So suddenly, hey, I might not know yet how it does it, but it makes a lot more sense to imagine the Earth is also orbiting in a circle around the sun. Now, there was another objection people were coming up with. They said, but, you know, it's so much simpler to say every object orbits around the same center. Every object orbits around the Earth. If the sun's the center of the solar system, then some things orbit the sun. Other things, well, the moon orbits the Earth. And that's weird and uneconomical and doesn't make sense. Everything should orbit the same center. So he turns his telescope to Jupiter, and orbiting Jupiter, he spots 4 moons. So yes, you can have different objects orbiting different centers because the moons of Jupiter are orbiting around that planet. So yeah, our moon could be orbiting around us. He still couldn't explain exactly why. That would be left to Isaac Newton 1 generation later. But you know, this did tell him, okay, Aristotle's physics needs to be breathed off from the ground up. He already knew that because it couldn't solve the problems he wanted to solve. But these were the arguments he was using to the other scholars of the day to show that Aristotle's physics had to be breathed off. And he was not shy about telling people when he thought they were stupid. His favorite way of publishing philosophical arguments was in the form of a dialogue. It would be a fictional conversation between 2 participants. I mean, this tradition goes back to Plato and the dialogues between Socrates and whoever Plato would be putting words in their mouth to oppose Socrates. Because in Plato's dialogues, Socrates always won. Plato was a serious Socrates fanboy. But in Galileo's dialogues, well, there would be one person who was a thinly disguised version of Galileo, and there would be somebody else who was a thinly disguised version of whoever Galileo was mad at the moment. And the conversation would be not exactly fair and balanced. One participant would end up looking very foolish. So he wrote dialogues on the Copernican versus the Ptolemaic world system. He wrote dialogues on how tides work. It turned out that his model of tides was just as wrong as everybody else's model of tides. Nobody understood how tides work. But man, did he manage to make a lot of enemies as he put forth these viewpoints. So he was accumulating enemies like a dog accumulates burrs running through a field. And he decided that that would be a wonderful time to decide to try to get Copernicus's books reinstated and thought of as the central way to think of astronomy. Because by this time, I told you in Copernicus's day, he had not received a lot of religious opposition from the church. And in Copernicus's time, the Catholic Church was the main religion throughout Europe. However, the Protestant Reformation was going on right as Copernicus was alive. Martin Luther lived at the same time as Copernicus. So by Galileo's day, wars were breaking out all over Europe, brutal, bloody wars between Catholics and Protestants for control of different territories. And in the middle of this polarized environment, suddenly nobody was very soft on heresy anymore. So now Copernicus's books were considered, the gateway to hell. And if you were caught reading Copernicus's book, you were very likely to be hauled before the Inquisition. So Galileo said, well, I got to change this. Went to Rome voluntarily and said, I'm going to appear before the Inquisition and convince them that Copernicus was right. Well, he did appear before the Inquisition. There was a cardinal. What was the name of that cardinal? I'm butchering his name a little bit when I call him Bernatelli, but a very educated guy who had actually been sympathetic to Copernicus himself before hardening his viewpoint and deciding that no, Copernicus just leads to heresy. And the cardinal, well, you read the transcript of the trial, most of it reads like a civilized debate between academics, except when the cardinal occasionally says, I think the time has come that we need to show you the instruments, by which he means I need to take you downstairs and give you a tour of our torture chambers and remind you who's actually in charge here. They weren't talking about astronomical instruments. So the trial went very badly for Galileo. He was warned never again to teach or publish or repeat or even think about these Copernican heresies. And Copernicus's books, which had been just kind of looked at with suspicion, were now put on the index of prohibited literature. So you couldn't publish them, at least not in any Catholic-controlled parts of Europe. The Protestant Church, not that it was any less authoritarian and devoted to rooting out heresy, but they just had a different set of heresies that they were interested in. Newton, a generation later over in England, would have no trouble with his Copernican views, but he would be routinely accused of witchcraft by the Church of England. So it's just kind of a different set of triggers for each one of those churches. But so Galileo was kind of forced to retreat back home and work on other projects for a while. However, as time went on, he got more and more bold about going ahead and arguing for the Copernican system. He would put a preface on each of his books saying, I'm not saying that anything in this book is physically true. I'm only introducing it as a mathematical hypothesis to do calculations from. And then the rest of the book was obviously saying, yeah, the Copernican model's physically true. What are you, stupid? You can't see that yet? Do I have to write a dialogue about you or what? So he began to attract some negative attention. He thought he had his chance, though, when a new pope, Pope Urban VII, came to office. And this was somebody who actually, back in earlier, younger days, had corresponded with Galileo, and they kind of had a friendship as they debated astronomical issues. Pope Urban was actually an adherent of the Ptolemaic system. He did think the Earth was the center of the solar system, but he said, I'm willing to listen to your argument. In fact, even though we've ordered you not to publish any of this stuff anymore, you have my dispensation to publish a dialogue where you explore both sides of this argument. All I ask is that you be fair to both sides. Apparently he didn't know who he was talking to. He said, in fact, I've got some arguments that I would like you to make sure to include in favor of the Ptolemaic system. And he kind of explained out his own arguments in favor of the Ptolemaic system. So Galileo publishes his dialogue, thinking, man, this will finally straighten everything out and get people to realize how stupid they've been. So he publishes a dialogue called the Dialogue of the Two Chief World Systems, and it's a dialogue between this philosopher named Sagaccio and one named Simplicito. And, well, the names, of course, in Latin mean exactly what they sound like, the sage and the simpleton. And he defended himself, saying, no, Simplicito was the name of a very well-regarded ancient philosopher, and I'm just naming it after him. And, yeah. Simplicito, meanwhile, was word for word repeating all the arguments that Pope Urban had made in his letters for the Ptolemaic system. And somehow, I still can't understand how, this caused trouble for him. So Galileo was hauled back to the Inquisition, this time in chains rather than going voluntarily, was grilled over the course of many days without sleep on his views, was forced to claim that he had never actually taken seriously the Copernican viewpoint and had only been using it as a mathematical toy and all the stuff he said in the introduction to his books, but they were like actually making him pretend he meant it. And in the end, they forced him to make a public recantation where he said his entire life's work had been nothing but foolishness and lies, and that he now saw the light. He was over 70 years old by this time. So this time they did take him on a tour to view the instruments. So they didn't actually torture him, but they took him to go to the torture chamber and look at all the instruments and see how they're used. And apparently that was usually enough to convince somebody to recant. And, well, Giovanni Bruno, Copernicus' student before, had all the same treatment and had not recanted and had been burned at the stake and had a few badass last words. They say he lunged toward the judge while he was in chains at his trial and watched the judge flinch backwards at the sudden motion, and he laughed and said, looks like you're more afraid to pass judgment on me than I am to receive it. So that was Giovanni Bruno. Galileo at age 70 was not willing to make that same move toward martyrdom. So he did make this humiliating recantation. They sentenced him to life in prison, and then shortly after that, they commuted it to house arrest so that he could go back to his home in Florence. They say that as he was being led out of the Inquisition chamber after this humiliating result to what he thought would be a great victorious trip to the Vatican, that he was heard to mutter in Latin, a per se move, which means, and still it moves. In other words, okay, you guys showed me the instruments, you win, I'll say whatever you want me to say. It doesn't make any difference, the earth still moves, none of us can change that. Whether he actually said that or not is obviously questionable. He'd have to get just the right balance between saying it loud enough for his supporters to hear him and saying it quiet enough for nobody else to hear him. But it's not something that was added in later centuries to the legend like we once thought it was. They actually have restored some paintings from that era, one of which was a painting of Galileo in his prison cell after the trial before they released him to go back to his home. And on the painter on the wall of the prison cell had written the words, a per se move. This was painted like 2 years after the trial. So apparently, even at the time, that was kind of a legend among Galileo's supporters. It was kind of the watchword. It's like the old film noir movies where the spies in trench coats meet under the street lamp and they said, the caged bird flies at midnight so that you know that you're meeting with the right person. That was apparently kind of a passphrase for the pro-Copernican scholars at the time was a per se move. Okay, we're both on Galileo's side here. So whether he actually said it, I don't know, but his supporters thought he said it. So what did he do with the rest of his life? Well, he went back home, continued working. He was by this time going blind, so it was harder for him to do experiments. But he did write 2 more excellent books, which he couldn't publish in his home country because one of the verdicts at the trial had been everything Galileo ever wrote, also everything Copernicus ever wrote, and for good measure, everything Galileo ever will write, we don't even need to read it in advance, is on that index of prohibited literature. So he had to have it smuggled after his death out of the country and published, I think, in Denmark, somewhere that was at the time in Protestant hands, so that the index of prohibited literature didn't matter. Of course, then you still wouldn't want to be accused of it being a book on witchcraft, but apparently it managed to slip between the cracks of all the competing systems. And the book did hit print And despite the best efforts of his critics, Galileo, well, he was thought of as a crackpot and an irascible and a difficult guy at the time, all of which was true, but it was not very many generations before he was also thought of as absolutely right, pretty much across the board. So this is what managed to finally get both astronomy and physics moving again after, well, in the case of physics, after 1,800 years of Aristotelian doldrums. Not that Aristotle was a dumb guy to have come up with that system, but it was just a system that sounded so right while being so wrong that it took somebody as stubborn as Galileo to finally shatter its grip on the public consciousness. With the year Galileo died, with a poetic handing off of the torch, Isaac Newton was born, and physics was off and running once more. Whew. Thank you for so much patience. I'd be glad to hang out and discuss anything people want to discuss, but I know you've got places to be, and this is about, like I said at the beginning, where I'd hope to leave off tonight. Kind of if we do another one of these talks somewhere down the line, the next phase will be, now that we got the solar system straightened out, what can we figure out about the stars outside the solar system? And again, hopefully take us through kind of the underpinnings of the Big Bang model in the 20th century. And from there, if you choose that you'd like to hear more, we can go on to dark